All right, so this is the last part that we covered last time. I have it here. So it was about invariant subspaces and the Cayley-Hamilton theorem. Let's try to remember about invariant subspaces. So we have a vector space V and the subspace W of V. It's T invariant if this thing holds. So when you apply T to anything in that subspace W, the result is still in W, which is something that is, cannot be taken for granted. It doesn't happen most of the times. But if W has this property, then it's called T invariant. All right, then we've seen some examples. So the simplest ones being the extreme cases, right? The zero subspace and the entire space V. Then we looked at the null space, we looked at the range, and also at the eigenspace associated to every eigenvalue. And then we reached this example, which will actually be very important, will turn out to be very important in this section. It is the idea of a T-cyclic subspace of V generated by a non-zero element x. Of course, if x is 0, then nothing happens, because if you keep applying t to x, you still get 0, right? So you get a trivial space. That's why the request for x to not be 0. Okay, so W is defined to be the span of all those vectors, x, t of x, t squared of x, and so on, where by square we mean by composition, so it's t of x, and so on. So we checked last time that W is T invariant, because when you apply T to a linear combination of things in that set, you end up with another element of that set. All right. Second property that this T-cyclic subspace has is that it is the smallest subspace of V that contains X. So in other words, W is the smallest T invariant subspace of V that contains the element X. What does this mean? Well, it means that if W is a T invariant subspace of V, with the property that it contains X, then it must contain the entire W defined above, so the entire T-cyclic subspace generated by X. Okay, so there is nothing in between that is T invariant between X and W. Why? Well, how do we show that? So we start with something in W, and we want to show that it belongs to W1, right? So let Z be an element of W. Show that Z belongs to W1. So what does Z look like? Well, it looks like a linear combination of all those things. Or some of those things. Doesn't matter how many of them. So why would this belong to W1? X itself is an element of W1, correct? So then any multiple of X, like A1 times X, is in W1. Because W1 is a subspace, so it's closed under scalar multiplication. What about this? Is T of X an element of W1? What guarantees that? This thing here. Isn't W1 T invariant? Yeah, so T of anything in W1, in particular T of X, belongs to W1. So then again, W1 is a subspace, so even a scalar multiple of T of X is in W1. Because it's T invariant. Okay, then if T of X is in there, T of X is also in there because it's still T invariant. So every term of this sum is an element of W1, which again is a subspace, so it's closed under addition. Therefore, everything belongs to W. Okay, so W, as above, defined as above, is the smallest with this property. All right, let's take a minute to look at an example to compute such a thing. So this W, the T cyclic subspace of V, is in fact, is the span of what seems to be an infinite set, right? Because I can keep on applying that T to X, to T of X, and so on. And I don't know what happens, but most of the times, nice things will happen. So this set will not keep on going. So here's what I mean. T, for example, from P sub 3 to P sub 3, so a linear operator on P3 of R that takes a polynomial into the second derivative. Find T cyclic subspace of P sub 3 of R generated by the element Z equals the polynomial X cubed. Okay. So we need to look at this W, which was the span of Z, T of Z, T of Z, and so on, right? So Z is X cubed. What is T of Z? Well, T was the second derivative, so 6X. Okay, so now when I apply T again, it's going to end up being 0. And if I keep on applying T, so the second derivative, all of them will end up being 0. So, the 0 vector can be eliminated from the set that you span because nothing new will be added. So W is just the span of X cubed and 6X. So, in the end, you can easily find the basis. The basis will be given by the first two entries, right, Z and T of Z. And we're going to see that this happens in general. So one of the main results of this section is that if you want to find the basis for the T cyclic subspace, all you have to do is to go up to a certain K. You're not going to skip any of them. So it's not possible for the basis to be formed by Z, T to the third, T to the sixth, T to the 11th. No. If it has to contain everything up to a certain point. We'll see this later on. Okay, so now a nice thing about this W is that if T is a linear operator, so linear transformation from V to V, and that and W, well, actually, it doesn't have to be the T cyclic subspace. It's just a T invariant subspace. Then I can look at the restriction of T to W. So what does this mean? It means that I'm only applying T to elements of W. Okay, so I'm defining this map on W. And where will it take W? What will be the codomain of this map? Well, when I apply T to something in W, what happens? Because W is T invariant, it goes back to W. So the nice thing is that the restriction turns out to be a linear operator or a linear transformation on W, which again, in general, might not be the case. Okay. Now that I have this idea of the restriction, here's what we can show about it. So T is a linear operator now on a finite dimensional vector space, V, and W is T invariant. Then the characteristic polynomial of TW divides the characteristic polynomial of T. Okay, so let's see what this is. So this is more of a technical result that we're going to need later on. Okay, so W is, after all, a subspace of V. Let's say it has dimension k, and V itself being finite dimensional, let's say it has dimension n. W is a subspace, so k is less than or equal than n. And let's say that the following is a basis for W. In particular, that set is a linearly independent set of V. Therefore, it's going to extend to a basis of for V. V1, V2, Vk, and then we'll add n minus k more vectors. Let's call this beta. Okay. Let's denote by A the matrix of T in the basis beta. Right? We have to prove something about the characteristic polynomial of T, so I need to, that is the determinant of the matrix of T in some basis, so I need to come up with a basis in order to talk about that. So let A be the matrix of T in this basis beta, and let B be the matrix of T in the basis of the restriction to W. Let's call the basis of W gamma. So the restriction is from W to W. Gamma is a basis for W, so it has a matrix. Let's call that beta. All right, so now we're going to look at the characteristic polynomials for the two transformations, T and TW. So the characteristic polynomial of T is going to be the determinant of the matrix of T in some basis like beta, so A, minus T identity. All right, but I want to know what this, how this A is related to B more specifically. So when you compute the matrix of T in the basis beta, what do? You do T of V1, right, and then you express it in terms of V1 through Vn. But T of V1, T of V1 is special because V1 was in W, right? V1 is part of the first K. So when I apply T to something in W, I land in W, correct? And that means that T of V1 is only a linear combination of the first K vectors, not of the remaining n minus k vectors, because the result is still in W. So what does that mean? Well, it means that it's going to be something in the first k rows here, right? The first column is going to maybe have some entries in the first k rows, but for sure is going to have zeros in the remaining n minus k rows. So if this would be the kth row, down to n is going to continue with zeros. Okay. And then I can think in the same way about T of V2, because V2 is still in W. So when I express T of V2 as an element of W, it's still a linear combination of V1 through Vk. So again, it's going to have zeros from the row k on. And we've seen this idea a little bit last time, you know, how to break this into block matrices. So in the end, I can keep on applying this argument up to the kth column, right? So up to T of Vk. So in this way, what I get here is a matrix, 0 underneath. This is a matrix C, and that's a matrix D. I have no control over those, right? So when I keep applying T to the vectors that we came up with up to n, we don't know what happens there. But the matrix, the k by k matrix that is missing in this picture will actually be what we called above the matrix B. Why is that? Because the matrix B is the matrix of the restriction of T to W. What does that mean? Well, it means that I'm only allowed to apply T to an element of W, but I apply T to V1. T of V1 is the same as the restriction of T to W of V1, right? Because V1 is in W, right? So up to the kth one, they actually agree, because that's what the restriction means. And B was the matrix of the restriction, so it goes up in that corner there. Okay, so if I go up here, this is the determinant of the following matrix. Okay, subtract T from the main diagonal, so you only subtract T from the diagonals of B and D. So when you compute the determinant, and that's something that will show up, as I said, in the homework assignment. I don't think it's there yet, but determinant of a block matrix that looks like this is the product of the determinants of the matrices on the diagonal. Okay, but this thing here, this is in fact the determinant of who was B. It was the matrix of TW of the restriction in the basis gamma. And by the way, this is not IN here. You agree? It's IK. All right, so that first one in fact is the characteristic polynomial, right, of the restriction of T to W. Okay. And then it's times something, right? I don't know what that something is. Yes? Oh, yeah, you're right. This is not even this one is k, right? What's that? N minus k. And by the way, I stopped seeing what I'm writing, so it's going to look very messy. I don't know, this has a big delay, so I don't see what I write, only after a while. All right, so what have we proved? We started here with a characteristic polynomial of T. We ended up with a product between this which turned out to be the characteristic polynomial of TW. So the product between that and something that I don't know what it is, but it doesn't matter because this actually proves that the characteristic polynomial of TW divides the characteristic polynomial of T. Divides the characteristic polynomial of T. And that is exactly what we needed, right? So we keep in mind that if W is T invariant, take the restriction, then you have this nice connection between the characteristic polynomials of the two. Okay, so now I'm going to go to what I mentioned before. Or not. No. That's like a new technical issue. I'll just wait 1 more minute and then probably move to the board behind. I know, but that will stop the entire session, which I could do and have a separate lecture. But... You mean like hard restart like this?
Yeah.
Like everything? Okay. It didn't. It was just. Hmm? Sorry?
Something behind that, it might be like a security block.
Behind what? It just refuses to do anything. Let's see. Oh. It doesn't do anything.
Oh, that's fine.
What? It wants
Might want it
update?
to update, so it's being mean to you until you do that.
Realize.